Just thought I'd record a quick video here just to clarify some questions that I've received regarding question 3 from theory assignment number 2. So in question 3, you're given a relational database schema with attributes A through E, and we've got a set of functional dependencies numbered 1 through 4 here, and we've got a decomposition for that relational schema. So we've got AB, BCD and ADE. We have to show that this particular decomposition is lossless, so we have to show that it has the non-additive join property, and to do that we actually we run through this algorithm, algorithm number 3 or 16.3 in the US edition of the text here, where we create some matrices and actually create attribute markers and pass them between our rows. Now I went through the example for questions for part C here, so in a figure 16.1 part C. We ran through this example where we were given our relational schema, so we have our employee attributes SSN, ename, we have our project attributes pname, pnumber, pname, plocation and hours, and we were given the decompositions R1 through 3, and we have our set of functional dependencies. Now in this example we performed the first step of the algorithm, where we substituted in all of the A markers into the rows for relations that actually contain those attributes. So for example, R1 contains the attributes SSN and ename, so we sub in an A marker, so we've got A1 and 2 here. R2 contains pnumber, pname and plocation, so we sub in the A markers, A3, 4 and 5 for those, and then R3 we sub in A markers for SSN, pnumber and hours. Now we went through that example and we got the set of results here at the bottom. So for example, if we go through, if we look at step number 4 in our algorithm, we can see that that for all rows in our matrix that have the same symbols in columns corresponding to the left-hand side of the functional dependency, so we're looping through our functional dependencies in this step, we actually substitute in rows that have an A symbol, so we move the A symbol to any rows that don't have an A symbol in them for the Y side of the attribute, if the columns share the value for the X side. So what that means is, in our example here before, if we start at the top, if we start looking at R1, we go through, we can see that it has an A value in SSN, and we can see that we have a functional dependency. So if we're looking at the functional dependency SSM and ename, we've also got an A value in R3's SSN column. Now if we go over to the ename column, we can see that in R3 we have a B value. So because we have a matching column value for the a matching row value for the SSN column for both R1 and R3, and R1 has an A value there, we pass that A value down. So we can see that that's why that one changes to A2, and we repeat that process for each of the functional dependencies. Now if we look at example number A, now we didn't run through example number A in the lecture because it's actually a negative example, and I wanted to sort of show you a positive example to introduce the concept. We've gone straight to the first step here and substituted in our A values. So you can see here we've got relations 1 and 2. We're looking at employee locks and employee project 1. Are our two relations, and we've got R1 has ename and plocation, so we've substituted our A values in, so A2 and A5 have been substituted in, and in relation 2 we've substituted A1, A3, A4, A5 and A6 in. So we've got all bar ename, which is a single B value, in relation 2. Now if we look through our algorithm, we'll start by looking at the first functional dependency, which is actually our ename value. So our SSN determining ename value. So if we go down from the top here, we can see that although R2 has an A value there for SSN, there's no other matches for the SSN column in any of the other rows. So R1, which actually has the right-hand side of the functional dependency, so it contains from our algorithm, it contains the Y side of our functional dependency. We can't pass that value down because R1 doesn't contain the A side. So if we go back to our description here, for all of the rows in S that have the same symbols, so we have to have corresponding symbols here, corresponding to the left-hand side of the functional dependency in order to copy an A value down. So by that particular rule, we can't copy the A value into this one. We've got similar situations with the other functional dependencies. So if we go to P number, we can see here that, that there's no shared attributes. If we go to, even though the P location is shared by the two attributes, we can't substitute anything in for P number there because it's on the wrong side of the functional dependency in the R1, and it's not in the R1 relation there. So in that situation, when we go through there, there's no change to that particular matrix, and as a result, these two, there's no column that has no row that has all A values in it. Hence, we've shown here that this particular decomposition does not possess the non-additive join property, and as a result, that's not lossless. So there has been some loss that's occurred when we've joined those two together there. So I hope that clarifies that quick point there. So when you're going through this particular example in question 3 here, it actually takes 2 iterations. You have to run through this inner loop here twice. So you'll run through to get to your answer. So just make sure you examine the functional dependencies carefully, lay out your matrix as shown in the examples here, and make sure you're careful and complete the first step with attention to detail there, otherwise you won't have the correct answer, and walk through that algorithm, paying particularly close example to step 4 here, in particular this first little section there. So that's all I have for today, guys, and if you have any questions about this about question 3 from the assignment, please let me know so that we can get those sorted out. Thanks, guys.